Hello, everyone. My name is Dale Brosius. I'm the Chief Commercialization Officer for IACMI, and welcome to Innovation Insights for November 2023. It's been a very fast year. We're already into November, but it's been a good year, and I hope that's been true of all of you that are attending today. So I'm going to give you a little bit of background. If you're an IACMI member, you already know all of this. If you're not, please reach out to us to become an IACMI member. We're organized around the themes of convene, connect, and catalyze. And I think today's presentations probably do a really good job of showing how that really works. The opportunity for co-funding, to participate in working groups, access to great facilities and expertise, and then education and workforce development. So broad product offering that we have. And so we hope that you consider joining IACMI if you haven't already. We just came off of a great CAMX 2 weeks ago. In Atlanta, a little over a week ago. Lots of great activity there. You'll hear from a couple of folks here that were all there and displaying what they had as well. So some great innovations on site, lots of interaction. Very, very happy for that. We're not done yet. We still have one more event that we will be supporting before the year is out. I want to give a big pitch for the Carbon Fiber conference that's supported by Composites World in Salt Lake City a week after Thanksgiving. So hopefully you can find your way there. It's always a really good, very focused conference on carbon fiber. And before you know it, it'll be the end of the year, and we'll be looking for JEC, just barely, after February. So we're a couple months into the new year. So IACMI will be there in force for that as well. And then just a little note here, although it's still some ways away, our summer members meeting will be in Indianapolis, August 13th to 15th of 2024. That portends to be another great event, as all of our members meetings have been in the past. So just a reminder that today's webinar is being recorded, and that all recordings of all previous webinars in this Innovation Insights series, going back a couple of years, are available on the IACMI website and on our YouTube channel. So please take time to go back and catch some of those if you've missed some really cool stuff over the past few months. Today we have 3 presentations from 4 presenters. One of them will be a dual presentation, and rather than wasting more time talking about it, I'm going to go ahead and introduce Kevin Line. He's the VP of Manufacturing for Rise Building Products, and this is a very, very cool application that cuts across a lot of themes in the composites industry and IACMI's infrastructure group. So Kevin, I will turn it back over to you.
All right, thank you, Dale. Share my screen and the presentation.
I'm trying to see if I can get back to mine.
Right, does that look fine?
I don't see it right at the moment.
Right.
Try pitching up there again. Yep, just need to put it in the slideshow. We'll be good to go. All right, and then swap, duplicate.
Wow, there we go.
Okay, thank you, guys. All right, good. Well, Dale, thank you for that. Thank you for that introduction. I'm going to spend a few minutes talking about Rise Building Products, our sustainability story, and what we can do to support and work with the composites industry. So, like Dale said, I'm VP of Manufacturing for Rise Building Products. So, in my brief, we're going to talk a little bit about Rise green storage products. I'm going to spend a lot of time talking about the raw materials and our manufacturing process. So I want us to think of Rise first as a building products manufacturer. So we are currently providing siding and trim and panels into the building materials market here in our region, as well as far away as East Coast in the United States. And secondly, what's really key about us is that we are a recycler of materials that would otherwise be destined for the landfill. we recycle materials that are very difficult to recycle otherwise. And then when we recycle these products, they become a circular composite product. So when we take a material in, it ultimately becomes something that can be recycled indefinitely into additional building materials. And we've been able to demonstrate that here in our plant to this day. A little bit of our history. We have a long history as a recycling company and a legacy in recycling. Our founder founded Fiberon, which was a recycled decking product made from low-density polyethylene, and launched Rise in 2015 to take advantage of some additional material streams. We've had this beta site here in Mankato, Minnesota, which is where I am, since 2018. And we've been fully commercialized for the last couple of years. Like I said, selling into this market here in the Midwest and as far away as East Coast. So a couple things about our green story, and I think these two superlatives really jump out to me. We think about our legacy, or our start was with recycling carpet. We've expanded that into a lot of different materials, but we started out looking at how can we take carpet out of the landfill. So every year in the United States, 56 square miles of carpet is put into the landfill, and that's an enormous amount of material. There's a lot of life left in that carpet, maybe removed from homes, renovations, whatever there might be. That material still has a lot of life and can be used for other purposes. Incineration, landfill, neither of those are good options for this product, and that's what we've done, is been able to turn carpet and lots of types of fibers, composite fibers, into far more productive materials. 94% of our finished product is composed of recycled materials. So there's very little new material required to make what we're doing here. Here's our product line. And if our product is lap siding, trim, and panel products. So these are, if you think of cedar siding, wood panels, maybe a similar product might be hardy board, hardy plank. So that's the type of products that we're making here. So these are finished, ready to use on construction sites, on single family and multifamily homes. We'll make a variety of products to support that industry. And here's how it might look when it goes up. It looks and handles like a wood board. So an overview of our process. I'll spend a few minutes here. We are, again, kind of emphasize the point, we're a truly circular process. We start out with these recycled materials. We resize those to fit our process. So our products, our raw materials can come in and whole products, sheets, any number of different forms. We grind those down to a specific fiber length. Then step 2 goes into our resin blending. We add our resin and our waterproofing agents. 3 is we create a continuous web mat out of that. I'll show you a photo of what that looks like in a second. That mat has our facer paper on both sides. Step 4, we move into our hot press, and in our under heat and pressure, we're able to consolidate that mat into finished product. It goes from 10 inches of loft down to 1 inch loft, or less, depending on the type of product. Next is we'll cut this panel. So we cut it in various stages. At this point, this cuts in a very similar manner as wood products. And then lastly is we finish and package, and it goes to market. If that product needs to be recycled, we'll take it right back into the beginning of the process, and we can start the whole process over again. And the next couple slides here is I'm going to kind of dive into what are some of those raw materials that we can use. So this is kind of our list, but I'll kind of jump right into it. So we initially started out recycling post-consumer carpet. This is carpet that was recovered. Certain states that have these recovery programs will then remove the backer, bale this material up, and send it to us. And then from left to right, what you're seeing is as the carpet is removed, the bales as they come to us in the middle photo, and on the right is after being ground and ready to be resinated. So this converts that carpet into a fiber that we can use in our process. Another pretty readily available material is in post-industrial automotive fibers. Now these are very difficult to recycle otherwise, because usually these Liners that go into trunks and headliners and floors of cars are usually composed of multiple types of fibers. It could include some low melt plastics, some polyester, some fiberglass, and otherwise these become very difficult to separate. So this is, in one sense, a composite material that we are then grinding up. So we receive it. It looks like the middle photo, and when we are complete with our grinding process and ready to be resonated, it looks like the photo on the right. Additionally, fiberglass. So this is fiberglass roll installation. And again, a post-industrial type product might be scrap out of the manufacturing process. There has been no real way to recycle this also. This is usually landfill. In our case, again, we go through the same process of resizing this material, grinding it up, and it's ready to be resonated. And then the newest addition to this, I'll spend a couple minutes here talking about this, is that we recognize that our process would work very well for wind turbine blades, as well as finished composite products. So a composite product being a collection of multiple types of fibers with a resin binder. Because we don't need to separate any of those materials, we can use them as delivered. Our process lends itself very well to recycling into like wind turbine blades or even scraps that come off of composite manufacturing processes or even composites in other industries. So we take these materials in the form you see there in the middle, so they're already partially shredded. We move them through our process again to grind them into smaller pieces, and we take the product as a whole. There's balsa wood, there's foam, there's various adders and fillers in this process. Again, we don't need to remove any of that to move to create our finished product out of that. So this again is a process, and a couple more pieces we've been able to use various waste streams that come out of the manufacturing process. This on the left is a flashing material that comes out of composite manufacturing. The photo on the right is raw glass that comes out of a manufacturing process. Again, for composites. So all of these parts taken as a whole. In the next couple slides, what I'm going to show is we're going to jump from grinding and this phase of the process to how the material looks as it's being formed. So this is a photo of our production line as we speak now. And it shows the layup of this mat over top the paper facer. So you can see right along the bottom, this is the paper. Now this is a continuous web. We lay it down in various layers. There's usually a core layer that comprises a variety of materials. And then there's a face layer, a top layer that is a shorter fiber and contains a slightly different blend of materials. And then before it goes into our hot press, we'll add one more piece of facer paper. You can see the next photo here is the process. This step is right before the press closes. See, this is a hot press. You see this top platen actually has the embossing plate on it that leaves that very attractive cedar grain or wood grain texture in the board. And this is the back or the bottom platen that the top pushes against. So this press will close and squeeze this for a matter of minutes under heat and pressure. It causes that resin to set up and ultimately creates the product, finished product that we would then go into the saw area. So this is where we take panels, cut them down to size, and then ultimately this is where they become the finished size that would go onto a home. So you can see the photo on the left is panels as they've come out of the press. Photo on the right is as those panels have been cut into narrow strips and would become the siding product that would be installed. So I'm going to flash here to the cross section of this product. So our panels, as they come out, are a consolidated mat of these various materials. So they themselves are a composite. They're composed of multiple materials. Our current product here, as you can see on the top, is comprised primarily of the automotive materials and the carpet materials. And then The photo on the bottom is a future product that incorporates additional fiberglass, and unless we really pointed it out, it would be very hard to distinguish one from the other. And that's kind of the power of the process that we developed here, is that we're very, very much agnostic to the types of, to the mix and blend of the raw materials. We can take very, mixed material streams, potentially even dirty material streams that would be unsuitable for other recycling processes. We can take all those streams and bind them up and put them into our siding and trim products. So lastly, I want to leave kind of on this slide and leave a few minutes for questions here. So Rise, as a growing company, we have an opportunity to continue to take in additional raw material streams. So as that kind of illustrated, we can use fiberglass, we can use composite materials, you can use composites with the resin, even with the foam, balsa wood, other types of raw materials that are, we don't need to separate those. We can put them straight into our manufacturing process. So this is an opportunity to continue to use other raw materials in our process, and we are very open to using, having conversations with others who would like to discuss waste streams, so we can make the composites much more sustainable product line. So with that, Dale, I think I've kind of gone through quickly.
Yeah, we got a few comments for questions. Works out perfectly. Yeah,
Perfectly.
yeah. One question that's coming: is hardy board using recycled material?
Well, I do not know. Can't speak to what other manufacturers use in their process.
Yeah, I'm pretty sure it's not composite recycled. It might be some waste concrete or something. Who knows? Cement. Yeah. Okay. One thing you didn't mention, and I think could be important, is what certifications you have and approvals that you have for using this on siding on houses. I'm surprised you didn't show any pictures of houses made with your material, because I know they're out there.
Yeah, we've got, and happy to answer that question. So
there it is.
Here's a house built, almost entirely from our product. So Dale, our product is certified under the International Code Council. So we have a engineering report and an ESR that's generally issued by the ICC, so that our product can be used as siding on homes. And so we have a full quality management system that guides our manufacturing. We take various required test data in order to ensure that our product is compliant with that. So it really all drives back to the acceptance criteria for siding that is issued by the Code Council. Those ESR reports are what allows us to be used as siding on homes, and in that, if you were either architecting or seeking approvals from code officials in those municipalities, those would be the types of reports they would look for this particular product.
Okay, I had a question come in the Q&A about the carpet and an previous experience of trying to use post-consumer carpet and risk of they were told they couldn't because of kind of hazardous waste. Are you able to get around that concern? Or is that?
Yes, it is our carpet. So we don't actually handle the carpet directly. The carpet goes through a processing centers, usually in the municipalities where they are collected. Those processing centers delivers to us, and there's no hazardous waste associated with it. There's no, we've gone through the SDSs and the testing, so there's no additional hazards associated with the carpet as it's delivered to us. All that's handled on the back end side.
Okay, all right. And then about mechanical properties, how do you guarantee consistent mechanical properties, or maybe if it's more of a minimum mechanical property that you guarantee? Yeah,
it is. There is minimum requirements, and that again comes from the testing that we've done with the certified labs that help validate our product with the International Code Council. So we do have to maintain minimums for the product, and then we do that on a sampling basis here at our plant. And we have a full quality assurance lab here that we use to guarantee those properties.
Okay, and I got one other question. One is about what kind of binder do you use? I mean, obviously you've got thermoplastics, thermosets, in the waste streams? Is it a thermoset binder? And then do you have any issues with how does it hold up in moisture? Obviously, if it's on a building, you presume that that's okay.
Indeed, yeah. It's a well-established thermoset that's used in a lot of construction applications. It's the same type of binder that goes into OSB and polyiso foam. So it is a long life permanent bond. And then we've tested it, as well as others have tested it for literally decades out in the field to ensure it's long life in outdoor environments.
Okay, good. There are more questions in the chat, and I'd appreciate if you go in and while our subsequent presenters are presenting, so we can move on here. If you could put your comments in back against those. They're in the chat.
Yep.
The Q&A question you got was answered, so would appreciate if you go through that and make sure that when you set it up, when you answer, you set it up to go to everyone, not just the hosts and panels. Okay. All right.
Perfect.
Appreciate it.
Thank you, Dale.
Thanks, Kevin. All right, we're going to move on to our next presenters. It's a tag team of Andrew Maxey, the CEO of Vartega, and Haley Marie Keith, the CEO of MITO, and they won a big ACE award last week at CAMX, or 2 weeks ago at CAMX, and I said, you really got to bring this out and present it, because this is truly a not just a tag team presentation, but a tag team of two innovative companies in our ecosystem that have come up with something really unique. So I don't want to steal all your thunder. so I'm not sure which order you present, but Haley and Andrew, so go ahead. You look good.
Thanks, Dale.
Yeah,
appreciate that, and appreciate the collaboration with IACMI. Also appreciate Kevin's presentation. That was awesome. You're doing some amazing things there, so definitely want to learn more about that. We are tag team. Vartega recycles carbon fiber, and it's a pleasure to connect with all of you today. Haley, you want to give a actually, let me do this. I've got a slide here. I'm going to tell you about Vartega really quick for those that don't know, and then Haley's got a slide on MITO as well. But Vartega and IACMI have a long relationship. Dale, as you can see here, was part of our ribbon cutting. Earlier this year, we moved into a new facility. We've got 82,000 square feet, and that's going to allow us to produce 2,000 tons per year of our recycled carbon fiber bundles, which has a significant...
I'm not seeing the slide move. Is everybody else?
Nothing on my end.
Okay.
Okay, give me a sec. Technical difficulties.
Yeah, I always love to see.
Haley, go ahead and talk about MITO while I'm fixing it.
Yes, I will. I will help you, since we're tag teaming. We tried to make it easy so we would do one presentation. So yeah, at MITO Materials, we functionalize graphene, a novel material that is stronger than steel, but nobody seems to get it to work at industrial levels, and that is what MITO specializes in. So we can make materials stronger, tougher, and lighter by functionalizing graphene and incorporating it into existing manufacturing processes with no change. And that is exactly what we did with Andrew and his process, which he will talk more about.
All right, Andrew.
Awesome. Thank you.
We got the second slide, so
we're off to a good start, hopefully.
Yeah.
So when we combine these materials, we can do a lot of really cool things from a sustainability standpoint. And that's the point I wanted to make here, was the greenhouse gas reduction, or the CO2 emission reduction, by using recycled carbon fiber, because it's much less energy intensive than manufacturing virgin carbon fiber. Also, it has significant benefits when you leverage these materials in vehicle lightweighting, because for every kilogram of carbon fiber recycled carbon fiber used in automotive, we're able to save another 42 kilograms of CO2 over the life of that vehicle. So certainly significant. Really quickly, to talk a little bit more about recycling for everybody, with the hope that you now see a new slide.
Yes, we do.
Okay, good. Awesome. Carbon fiber recycling historically has been very small compared to other materials like metals or even lead acid batteries. And as Kevin showed, there's a lot of really difficult composite materials to recycle. Our opportunity is to leverage that with the high value material of carbon fiber. So Haley, there we go. There's your slide. I want to let you talk about MITO and talk about your stuff. Go ahead.
Yeah, so like I said at MITO, we functionalize. We have a novel chemistry platform that allows us to do surface chemistry on graphene and other 2D related materials. And the way we see ourselves in the market is really helping composite manufacturers and product manufacturers utilize graphene as a material. And when we do that and we work with our partners, we want to make sure that not only will it disperse into your system, but it's going to be easy to integrate into your existing manufacturing process so that you can realize and unlock the promise of graphene. And that's really how our collaboration with Vartega came about. If you're interested in using graphene, we have additional products that are not used with Vartega, which is primarily Ego, utilized in sports and rec, and has shown ability to lightweight other composite materials like golf club heads and fishing rods, which you may have seen at CAMX, as well as skis. Anything with fiber reinforced composite manufacturing systems, those products can go into the resin or on top of prepreg and really realize some very significant changes, improvement in strength, toughness, as well as lightweighting capabilities. But with Vartega, what we're talking about today, we actually developed an entirely new product to work within Andrew's system of recycling carbon fiber. And we saw this as a unique opportunity to see if we were able to coat graphene onto the carbon fiber through the sizing agent. So we developed what we are now calling Ligra, which is liquefied graphene. It's a water-based solution. And we were able to introduce that into the sizing process at Vartega to coat those carbon fiber, to coat the recycled carbon fiber bundles, and then put that into a plastic part.
Awesome. Thanks, Haley. So for those that haven't seen our products before or not familiar with Vartega, really our one of our secret sauces is our Easy Feed bundle. That's the format that we've commercialized in our new facility. We're able to take discontinuous carbon fiber, whether it's our recycled carbon fiber, can be post-industrial manufacturing waste, can be even pyrolyzed carbon fiber from others, and we can consolidate that into a format that has high bulk density and is easy to flow into thermoplastic extrusion applications. So we've got compatibilized binders, polymers, urethane, polypropylene typically, that we'll use as a sizing or a binder to hold those bundles together. And as Haley alluded to, we're able to incorporate MITO's Ligra functionalized graphene into that sizing chemistry, into that binder. So it actually adheres directly to the fiber and helps to further compatibilize with the polymer resin that's going into the thermoplastic matrix. So we did that, and for CAMX, wanted to show a little video that the MITO team put together. Hopefully the audio comes through. So together we introduced Fenix Fiber Plus to CAMX. Stand by for the next Hunger Games movie, because I'm sure it's going to be highlighted there. As you can see by the amazing graphic there. But the cool thing there is it allowed us to differentiate our product offering a little bit. We've now got a good, better, best product here. And with MITO inside, Fenix Fiber Plus has not only premium performance, but other benefits around sustainability that we can talk about in the future as well. So this is really cool for applications where you need that increased performance, and there's different pricing structures, of course, across these different products as well. So the cool thing was we were able to take that to CAMX and report out on some data on those materials, and we were really excited about the performance and a couple of the key criteria, specifically elongation and impact toughness. Flexural strength was also improved, and then the governing material for the modulus is actually the fiber, because carbon fiber is so stiff to begin with. But we were really excited about the performance improvement that we saw from adding the Fenix Fiber Plus, or the MITO material, the Ligra material, to make Fenix Fiber Plus. And this is just kind of scratching the surface. We're going to do a lot more development. This particular test was in a 20%. It was 20% carbon fiber in nylon, but we want to explore in polypropylene, do different weight loadings, and evaluate different criteria like connectivity and damping properties as well. Haley, you want to talk about the award, the ACE Award?
Yeah, I mean, so I think that that data and this collaboration really opened our minds to how we can utilize these recycled materials, recycled carbon fiber specifically, into new markets. So Andrew's talked a lot about what it looks like in the automotive market to utilize recycled carbon fiber through his process with the easy feed bundles. And I think when you look at the improvements in performance, you're able to open up new market opportunities that weren't looking at recycled materials before because maybe they thought there was a sacrifice in performance, but now they're able to look at it with a more serious understanding that it can solve for some of those mechanical improvements and really get the increase in performance without sacrificing in sustainability. And so we used those ideas and to apply for this market growth and infinite possibility or market growth category for the ACE Award, which is the Composites Excellent Award given at CAMX. And the category we specifically targeted was infinite possibility for market growth, because we believe that by upcycling these materials with novel additives like graphene and functionalized materials, that it can really open up new possibilities in different markets and a lot of opportunities for application. So we are super thankful for our collaboration with IACMI in this project specifically, because as you can see here, these panels that are in front of us on the table are actually interior components for an automotive door frame. And they were made at University of Tennessee, Knoxville, with connections that we had through IACMI. Students were truly working up until the last minute to get these panels made for CAMX. And it was an amazing feat just to collaborate with all of us together to showcase what this material can do. And the parts looked fantastic. As we mentioned, our goal at MITO is to drop in to current manufacturing processes and just impart improved mechanical performance and opportunities for sustainability, which I think was all captured really well as we won the ACE Award this year.
So specific thanks to Composites One for sponsoring that, and obviously to Dale and the IACMI team. And then several folks at AUTK. I've got Pratesh, George, Stephen, Abdallah, and Uday. And hopefully I didn't miss anybody, but I know there's a whole team of people that make those things possible. So thank you guys for the efforts there. Now, yes, the collaboration isn't going to stop just because CAMX is over. The ribbon and the award are nice, but where do we go now? Well, we continue to collaborate on development. We have at Vartega, our facility in Colorado, we've actually invested in compounding capability, injection molding capability, and characterization. MITO also has quite a few characterization assets. So we want to take this, the next steps to build out the data set around these materials and identify additional applications. So we're both happy to help with application development as we look at new markets and new opportunities, and can help accelerate that because we have these assets in our facilities. So feel free to reach out for further discussion around how we can help. And as we do that, to kind of come full circle on the sustainability piece, I can tell you year to date at Vartega, because of recycling carbon fiber, carbon fiber is crude oil based, and we use significantly less energy to create our easy feed bundles than to manufacture virgin carbon fiber. So this year we've already offset 5.2 rail cars of oil. So as you're sitting at that railroad crossing and you're seeing those tanker cars go by, just think about all the recycled carbon fiber that we can help you incorporate into your materials. So thank you for your interest. Haley, anything you want to add to close us off?
No, I mean, I think this is a really great, Dale, thanks for the opportunity to present at Innovation Insights. I know Andrew and I have both presented our technologies differently in this cohort before, but I think it was an amazing opportunity to present together to showcase truly what IACMI is all about, right? Connecting, convening, and catalyzing new innovation. And Andrew and I have been talking about doing this for a long time, and we're excited to see where Fenix Fiber Plus and the different plastics that we're looking at characterizing and compounding into, what markets and applications we can unlock through this collaboration together.
All right, great. So time for a couple of questions here. And we've got one that came in. It says, looks like your focus, this is to Haley, your focus is on thermoplastics. Have you done any work with thermosets? And if so, which ones?
We actually focused more on thermosets originally. This is our real first delve into thermoplastics through the addition onto the fiber. So we have worked in thermosets extensively, and we can work with you on your specific polymers, but off the hand, we work within epoxies and carbon fiber and fiberglass reinforced composite systems with different manufacturing methods. We can go spray onto the pre-preg with our material. We can go into the resin and then create pre-pregs and tapes. We've worked with polyester and vinyl ester resins, like I said, as well as epoxies. And yeah, we have a lot of data that I can share on that. If you would like to talk with my team, happy to do so. That we have a lot of data there that in the thermoset areas with graphene.
You know, some things in coatings and adhesives as well.
That's true. Yes, we're working with coatives and adhesives formulators currently. Graphene has a lot of unique properties. One of them is thermal conductivity and electrical conductivity. So the ability to decrease open time on adhesives has been significant. And in the coating space, there's some antimicrobial properties that graphene oxide provides. And so we're working with clients there to work with their formulations to kind of unlock those properties and get them to disperse accurately within those systems.
Okay. Andrew, yeah, you did mention polypropylene, and that's always been one of the tougher polymers to maximize fiber properties with, and so the holy grail is kind of like, can I get polyamide level performance with polypropylene, where I don't need quite the thermal results, but all the other properties I need, so how are you coming on that?
Yeah, great question. Most of our applications in polypropylene supplies, surprisingly enough, have been in additive manufacturing thus far. We've had a lot of good success with a partner in 3D printing, which is notable because the stability of the carbon fiber helps the polypropylene to not warp during the 3D printing. But to your point, polypropylene for automotive lightweighting is going to be really important. We have done some work there. I would say the performance is good. But there's still room for improvement. And that's where a material like Lygra can be really interesting, because we've got the mechanism now to get it onto the fiber, and evaluating how to get that performance at a loading level that makes sense for polypropylene is going to be really interesting. So there's still work to do there. I hope within maybe at the next CAMX we can present those results.
Absolutely. Yeah. And I would just add to that, we have some data of our graphene material in the polypropylene resin in the thermoplastic sets. And we've seen improvements in strength and tensile. So I think that going on to the fiber with the collaboration with Vartega, we should be able to add and increase that opportunity through that delivery mechanism. So graphene in polypropylene does have some of those improvements that you're discussing. And I think together on the fiber, we can enhance that as well.
Okay, so while we were chatting there, another question came in is what kind of sizing did you apply onto the carbon fiber, considering that fibers could come from different sources? So,
yeah, so we evaluate the different fiber types and different chemistries that are on the fiber to begin with, and then compatibilize with various sizing. So it depends on what thermoplastic or thermoset we're going to incorporate the fiber into. But oftentimes we're using a urethane or a polypropylene sizing compatibilized. Okay. But really, there's no limit. I mean, we can incorporate a lot of different chemistries onto the fibers.
Okay. So yep. So Kim answered the question that Rick wanted contact info.
Yeah.
So somebody came and said, "Hey, how to get in touch?" So Kim's going to take care of sending contact info for both of you to him.
Thank you.
All right, so appreciate it. Yeah, great presentation as always. Congratulations on the award, and very excited to see where this goes from here. So thanks again.
Thanks, Dale. Thanks, everybody.
Okay. All right, and we're coming to our third presentation of our trio today, and very excited about this one too. Again, we're gonna jump in a little different direction, but and go into the continuous fiber phase, but with Christopher Oberst. Chris is the president and chief engineer for Weave 3D. So when I saw this application that he's going to talk about, before, and we've known Chris for a long time, but seeing this reduced to practice, said we really got to get you on and talk about it. So Chris, take it away.
Thanks, Dale. Really appreciate it. So everybody, just kind of for your reference, Weave 3D, kind of like Vartega and MITO, we're a startup. We spawned at Georgia Tech back in 2017. I had done my PhD in materials science there, and we're still based in the Metro Atlanta area today. If you don't know us, we are a manufacturer of composite lattice materials, and I'll talk a little bit about that when I get into this, but our sort of core focus areas are automotive, which is about 80% of our focus, and construction, just about the remaining 20%. And conceptually, what we're able to do, and what I want to talk about today, is this concept called rebar for plastics. which allows us to produce a cost-effective, scalable, and locally tunable composite lattice material that is suitable for mass production. So just a little bit of an outline here. This presentation is kind of a hybrid of one that I presented at CAMX. So there's a little bit of kind of academic background on what we call design degrees of freedom and structural and mechanical properties. And then I'll go into sort of what rebar for plastics the concept is, and then to what Dale was alluding to earlier, we'll talk about our recent automotive beltline stiffener case study that we did with Braskem. So design degrees of freedom, this is a principle in a component level part design, which basically says if you have a material and you have a part geometry, what levels, what variables effectively can you adjust in order to change the part level properties? So we're talking about things like load capacity or part level bending stiffnesses, those sorts of features. So kind of the simplest possible version of this is something like sheet metal, where the part, curvature and things like that may be defined by the application, but by changing the gauge of the sheet metal, so the thickness of the sheet metal, you effectively change the stiffness and strength stiffness and load capacity of that material, even though its strength remains the same and its modulus remains the same. So when we talk about a single degree of freedom, what I'm generally referring to is you have a homogeneous material over the entire surface of the structure, and you are just changing thickness. We then can talk about 2 degrees of freedom. So this is oftentimes things like injection molded plastics, where you have ribbing, or even laminate type composite structures where you can change the amount of plies in different areas of the part. Again, we're saying, hey, 2 degrees of freedom is a homogeneous material, so one material over the entire part, but we're changing thickness in different areas, and we're changing the distance between those thicker regions. So now we have some extra variables that we can play with. Now, 3 degrees of freedom is traditionally the limit for most composite designs. This is things like back-injected laminate structures, or things like composite laminate stack-ups with cores or other mixed materials, where you might have a ply of glass fiber and a ply of carbon fiber and then a core, and then so on and so forth. So you're now looking at being homogeneous within each layer of the structure, but you are effectively heterogeneous through the thickness of the structure. So you have some different materials potentially in the structure. Each of those different materials can have different thicknesses in different areas, but within their own layer of the structure, they're one material. So what we're going to be talking about here, and what kind of our rebar for plastics concept unlocks, is what we call heterogeneity within the layer. So effectively, within a single plane of this composite, we can change the mechanical properties by changing the local spacing of that material within that plane, as well as by mixing different types of materials into that structure. And then we're still kind of combining these lattice reinforcements that I'm going to talk about into other plastic parts. So you have sort of a bulk material, and then within your reinforcing material, you have multiple different types of other material properties. So you effectively get a regionally tunable performance throughout the structure. So looking at something like material properties versus structural properties, I kind of mentioned that in the opening here, where things like modulus and strength are normalized, so they're per unit area, or things like toughness are per unit volume. But then you also have structural properties, which is how the part itself behaves. And these are things like bending stiffness or load capacity that are influenced by both material property and geometry of the part. So one of the simplest examples of this for bending stiffness is for a simple rectangular cross section, where the bending stiffness is a function of modulus E and I, which is the second moment of area. And that I is defined by the width of the part times the cube of its thickness. So what this effectively means is if you double your modulus and you keep the geometry the same, you double your bending stiffness. But if you double your thickness and you keep the material the same, you get an 8 times increase in bending stiffness. This is part of the reason why injection molded parts use ribbing, because it provides them with extra bending stiffness at a material efficient way to do it. So the way that this can kind of be applied in these rebar for plastics concept is through something called composite beam theory. So we're basically saying, hey, you can use ribs or ply stacks of two different materials, and you can actually convert these two different materials into an effective eye of one material based on the ratio of the two materials modulus. So what that looks like practically speaking is, let's say you have a material 2 and a material 1. You want to convert them from one to the other. The effective cross-section of that material 2 converted into material 1 is the original material's cross-section times the ratio of the modulus. So what this looks like kind of in an effective area calculation, if you were to have a plastics material as your base here, what I'm showing is the this sort of neutral axis number, the dashed line here. That neutral axis is for the original material. I then add a layer of composite on the top and bottom. I convert the original material into an equivalent area of the composite material, and my equivalent area looks like an I-beam. If I then take that neutral axis and I apply that material only to one side, and I apply the same number of layers, so 2 layers to one side, you'll notice the neutral axis comes down, which means that it's less efficient to add material to one side versus both sides, but your equivalent cross-section is a T-beam. So you're basically getting sort of a virtual structural shape by having these two different materials in the structure. This is also why in a lot of laminate designs, we use core materials. They're basically doing the same thing by creating these sandwiches. So one of the challenges, though, when we're talking about laminate construction, and when particularly things like organosheet, which is what's kind of the back half of this presentation will focus on, the problem is that the laminate is basically building both your thickness of the part and the material properties of the part. So if you then overmold that laminate with ribs, you're effectively putting a cheap material on top of a very expensive material, and that expensive material is still making up the bulk of your cross-section in the part, which means that you've got a lot of expensive material basically sitting in the mid-plane of your around the neutral axis, and it's not fully being utilized to carry the normal stresses in bending, which are sort of the tensile and compressive stresses that it really wants to carry. Rather, it's being loaded with shear stress, which for laminates is a problem because they want to delaminate when they're subjected to severe interlaminar shear. So kind of this is how we came into this process. Is we were looking to develop a new type of composite forming process that would be suitable for high volume production. We came up with what we call rebar for plastics. And what this is we take a thermoplastic unidirectional tape. These are commercially sourced materials. We don't do any of the tape production ourselves. But we convert these tapes using a proprietary forming machine into lattice structures, similar to what you see down here on the left. And these lattices can then go into conventional plastic molding processes like thermoforming, compression molding, or injection molding. And the resulting part that you get is a hybrid of this structural skeleton created by the unidirectional tape and the thickness buildup that you get from the molded plastic part. So you can kind of see this in the top right corner here, where we have a heterogeneous structure that is 2 different types of tapes. In this case, it's a natural fiber polypropylene and a carbon fiber polypropylene. And the carbon fiber polypropylene actually has variable spacing, so it's denser in the middle, then the spacing goes a little bit more sparse as you go to the edges. And this kind of localized tunability gives you a lot of control over where you put the material and how much material you use. So to give you a practical example of that, this is the automotive beltline stiffener part that I mentioned earlier. This was originally developed by Clemson Composite Center as part of a Department of Energy project that they received with the goal of trying to redesign a steel door into an all-composite door with a 50% weight reduction. And their original design concept called for using a carbon fiber nylon 6 organosheet, woven organosheet. And they were going to mold this organosheet and then trim out all of the window areas and things like that. So as you can imagine, if this is your part here on the right, this is starting from a large rectangular blank, you're going to have a lot of waste. So we came into this project and in partnership with Braschem, and we wanted to propose an alternative of, can we redesign this part into polypropylene, but using a lattice structure to optimize the amount of material used. So kind of where we started here is we did some flat panel studies looking at different combinations of plastic material and lattice reinforcements. So different types of lattice, glass, carbon fiber, mixes of the two, as well as different spacings of patterns. So these two carbon fibers that you see here, one is a high density, one is a low density spacing. And we plotted these in a stress strain curve versus the reference organosheet material. So if you look at this light blue line here, the organosheet has a very good modulus and a fairly high yield strength. But once it yields, it fails basically catastrophically in a brittle failure mode. So it has no additional energy carrying absorbing capacity after that first failure. What we noticed with all of these lattice reinforced parts is the way that we had set up this structure where it was a sandwich of lattice, then pure polypropylene sheet, then lattice. What effectively happened was the top side of the panel would have a compressive buckling, and it would give you this kind of progressive damage zone that you see here, and then it would plateau. So you would actually be able to continue loading the part, it would continue absorbing energy, continue deforming. And we actually had to stop these tests because we reached the limit of the fixture. So we didn't actually fully break any of these panels. But even with just this data set, we were able to show that by tuning the types of materials that you use and how much you use in which areas, you actually can change that stress strain curve pretty much any way you want it. So you'll see this, orange one here is a glass design. It's actually stronger than the carbon fiber design, but it's less stiff. Whereas the one that we actually ended up settling on was this design D, this dark blue line. It has the same initial modulus as the carbon fiber organosheet, but it has a very wide progressive failure zone due to the fact that it has both carbon fiber and glass fiber in it. So they basically fail sequentially, carbon then glass. And then it has a pretty solid plateau region afterwards. So we're getting a lot of energy absorbing capability here. So we took these flat panel results, and then we did FEA analysis on the actual part itself. And what we noticed is that there's a really high region of stress here in the middle of the part, as you would expect. This part is designed to be able to withstand a side pull impact on the passenger or driver's side door. But there's very little stresses on the A and B pillars because these are glued into another component. So we actually realized we don't need a whole lot of lattice reinforcement in this area above and below that middle sash. We can effectively just use the middle area for the high density reinforcement, and then we can use less material in those areas that we know we're going to get trimmed out at the end of the day. So what this kind of looks like from a overview perspective, our manufacturing process, we're producing a lattice material. So it's going through our process as a tape, it comes out fully consolidated. We then did a lamination process, as I mentioned, making sort of that sandwich of lattice, polypropylene lattice. And then we formed with a thermocompression process the actual part, and then we did a water jet trim to finalize the geometry here. So the advantage of this approach is that compared to a carbon fiber PA6 organosheet, we were 50% cheaper, actually cheaper than a glass fiber organosheet. And that glass fiber organosheet did not meet the performance requirements, whereas our solution does. And we were even 20% lighter than the carbon fiber organosheet, which is kind of shocking. The key thing though here is that we were able to improve the yield of this panel in terms of mass in versus mass out. From 25% in the organosheet to about 45% in the carbon fiber or in our solution. And that resulted in about a 63% reduction in trim waste. So not only is this lighter and cheaper, but it's also a more sustainable solution in terms of reducing waste to landfill. But we weren't really satisfied with just doing that benchmark against the organosheet. So we also took that same design and modified it slightly where instead of using a pure polypropylene material for that middle, we actually used a natural fiber nonwoven mat. The total thickness of this panel was about 2.1 millimeters. By comparison, the one that I showed on the previous slide for the actual belt line was about 2 millimeters. But what we were able to demonstrate is that this same lattice reinforcement pattern compared to something like 20 gauge stainless steel was 1.8 times stiffer, 3 times higher bending load capacity, and 65% lighter. And just to compare that against the natural fiber on its own, just to show you that the lattice is doing all the work here, that's the force displacement curve for the natural fiber mat by itself. So our solution is 25 times improvement over that natural fiber mat. But the other important thing that I think a lot of people don't realize with thermoplastic composites is the amount of recovery capacity. So all of these samples that you see here were loaded to that 25 millimeters total displacement. If you look at these panels after what happened, that steel panel is permanently deformed. So effectively, if this was a door of a car and you got into an accident, that door is now crushed into the passenger compartment, and it's going to make it difficult for the passenger to exit the vehicle. Whereas if you look at our solution, we can actually show that after taking all that 25 millimeters of deformation, it springs back to within just a few millimeters of its original shape. So that's going to be much easier for someone to get out of the vehicle because it's no longer this kind of crumpled mess of material. And then kind of summarizing here, why use a composite lattice in general? Depending on what we're comparing against, whether it's metallics or plastics or organosheet, we're offering anywhere between a 30% to 60% weight reduction versus conventional solutions. We can locally tune these geometries. And this is a cost-effective automated continuous forming process that is compatible with existing molding processes. So it's really intended to be a high-rate industrial technology that is suitable for high-volume automotive manufacturing. And then, if you guys are interested in learning more about this, please reach out to us. I showed you kind of the automotive beltline part for the body structures application. We're also doing a lot of work with sustainable interiors. So if any of these kind of catch your fancy, let us know.
Thanks, Chris. Great, great presentation. A couple of questions. We've got a couple minutes here before we round up. Hey, somebody commented, very cool. How about thermal performance and elevated temperatures? So, go ahead.
Yeah, so it's a great point. So the reason why we did polypropylene in this particular part is that there was no thermal reason to pick nylon in the original case. They picked it because it was an available material that was compatible with carbon fiber that they wanted to use. One of the advantages of our technology is that because we use commercially off-the-shelf tape materials, we are completely agnostic to fiber type and polymer type. As long as it's a thermoplastic, we can run it as a tape. So we do a lot of work with things like nylons, even PPAs. I've done some of my original thesis work on PEEK and PEC materials. So we can effectively match the lattice reinforcement to the environmental requirements that this part will need to meet. So if you have temperature issues or fire retardance issues or things like that, we will work with you to basically pick the material that is compatible with that requirement.
Okay, so the new design on the Braskem part, or the part at Clemson, was there a test of that part done? Was it put in a fixture and then impacted, or?
There was. So we don't have a full-scale crash system at Clemson. We're working to see if the OEM sponsor for that project would be willing to do that themselves with their facility. But we did do some high strain rate flex testing, and we demonstrated that the lattice reinforced part had the same stiffness response and max capacity response as the original organosheet part. So that work is still getting some final data analysis, and we will probably be presenting that at Antec next year. But the preliminary work so far has been very favorable and validated our FEA simulation quite closely.
Okay, what's the cycle time for producing parts?
So this one's a little bit of a hodgepodge because we had to sort of do the lamination at one supplier and then do the forming at Clemson on what is effectively sort of a prototype line. I believe our total cycle time for the forming step was about 3 minutes. And most of that time is just the dwell time in the oven. So depending on how that's been tailored, you can bring that down. I think practically speaking, 2-minute cycle time is pretty doable for this. And then if you had set this up as kind of a linear work cell of laminating, forming, and trimming as subsequent steps, each of those steps could basically be done in the same time that the previous step took. So you could have a sequential production line.
Okay, well, perfect. We've hit the end of the hour. And, you know, I want to, show my appreciation to Kevin, Andrew, Haley, and Chris for, you know, 3 excellent presentations. Again, knocked it out of the park this month. Our next episode, we will do one in December. It's December 18th, so that's a week before Christmas Day. And we hope to see you attend that one as well. So more information to come. So thank all of you for your time today, and have a productive week.
Thank you, Dale.
Thanks.